We have derived the Navier-Stokes equation. We have discussed the unknowns to be determined, the pressure, the velocity components, and so on. And of course, we will try to show the application of Navier-Stokes equation for different fluid flow conditions, for different fluid flows, different geometries, and so on, at least a few of them, only to demonstrate that how do we affect them, how much useful they are in our real life. And as you know, that fluid flow, fluid mechanics is an important consideration as far as the human life is concerned, and it plays an important role in our everyday life. You know, there is a phrase that where there is fluid, where there is a human life or human existence, there is fluid. So things that are related to fluid flow, we need to know how to solve them, how to attack them, and for this, one of the tools available to us is Navier-Stokes equation. The four things I mentioned earlier: the pressure, the velocity components need to be determined from the given conditions. Now we will demonstrate this by solving initially some very simple problem from the given flow field, and then we will come to more difficult problem also. But we start with simple conditions, as is always the case. You will notice that the pressure gradient in this equation, which is Navier-Stokes equation, if I write it as dV by dt, they are equal to minus gradient of P plus rho G plus mu del square V. You note here that P does not appear in these equations separately or independently. It always appears in equations of motion as a gradient. So that is why they have shown here in an enlarged position to show its importance, that the fluid motion, when it occurs, then the absolute value of the pressure does not matter. What matters is that the pressure difference that exists in a fluid flow field at different points. Or we may also describe the same thing by saying that the pressure gradient, this is gradient of pressure. The gradient of pressure plays the important role, and the motion at times you will see many fluid flow where the fluid motion takes place only because of the gradient of pressure or the pressure differences that exist at two different points in the fluid flow conditions. And this is the same thing is emphasized here. So we describe this we start with simple problem and then we see what happens. These are some graphs showing the pressure difference behavior or the fluid flow action because of the pressure differences. The first problem that takes place is by considering a simple problem in which we need to calculate the pressure field in Cartesian coordinates, where the velocity field is given by this. This example, these numbers, sometimes I have mentioned you times and again that these refer to the book that I have prescribed for this subject, Fluid Mechanics, which I am following mainly, but there are many others also considered as recommended books, Fluid Mechanics by Professor Yunus Sengel and Professor Simbala. This book have been made available to you, but if some student has not got it or cannot access to that, he can always write to me and I will send him through email the same book that we are following. And as is always the case, that for a course we have to prescribe a certain standard textbook for a course. This is a course that is being followed in many international universities as a standard textbook for this course. So here we consider this equation. The velocity has been given to us and we need to calculate the pressure that is not given to us, that is not known, and only as a function of x and y, because the velocity field that has been given to us is only u and v component and there is no z component. I can see the unit vector I can see the unit vector j, I cannot see unit vector k. So only two components, and therefore if we calculate pressure, we can also determine pressure only in terms of x and y. And so pressure fields is to be known. And formally, the assumptions that we are making are that the flow field is steady, the fluid is incompressible, the fluid is two-dimensional, and the gravity does not act either in x or y direction, because in the velocity field you do not see any contribution coming from the gravity. So important to note down these things and to write down the conditions under which a particular fluid flow being considered and the solution is being looked at. And so because they play an important role in the solution, and the solution will reflect only those conditions that are assumptions that we have made. This is very important. It's a general solution, it will not be a general solution that applies to all kinds of flow. It applies to only specific flows. So first we check whether the given flow field satisfies the continuity equation or not. From the given flow field, which is given to us, and that is ax plus b and minus ay plus cx. So when we check that, then we see, when we write down the components, the partial derivative of x gives us only a. The partial derivative of b gives us only minus a. And z component is not there anyway. This is a two-dimensional motion. So we have a coming from this part and minus a from this part, the summation of which gives us 0. That means the continuity equation is identically satisfied. And so as far as if the continuity equation is satisfied, it means the mass conservation law is preserved, and in fact some of these parts we can use to find out the other component, the unknown components. Now we look at the component in the x direction, for example, and if I try to see the Navier-Stokes equation and I try to write down here only the y component. This is, for example, I could have written the x component, but only first we try, let us see for y and see what we get. Then we will apply it to the other component also. And remember, we are only considering two-dimensional motion. The contribution coming from here is, since it's a steady motion, a differentiation with respect to time will not contribute anything. We get 0. From this part, the differentiation, we obtain this number, and v by dy we obtain this contribution, and of course the z is not there, so that is 0. And from here we will have again 0, so this disappear and simplifies. So the only non-zero terms that we are getting are either from here and this one. So 3 terms. All other terms are 0. So the y momentum equation reduces to dp by dy equals these terms, rho into minus b minus a square into y. And likewise, when we calculate the x momentum terms, the x component terms, we will have a similar equation, and that gives us this. From these two, we integrate this part with respect to y and this part with respect to x to be able to obtain 2 terms for p, and then we equate them to get the answer. We try to find out. Now p is not a function of time because the motion is steady, and when I try to find out dp by dx and then try to differentiate again with respect to x, I get a 0. So I mentioned that we try to, the 2 terms where I have non-zero terms are dp by dx and dp by dy. I integrate from 2 to obtain a term of this type. When I integrate the y term from the equation, I can have p of these terms plus constant of integration, and let that be g of x. Then I differentiate the same thing with respect to x to obtain this. And from these two, dp by dx and from dp by dy, I can try to obtain the value of p. Now, when I differentiate with respect to x, and I am in fact trying to differentiate the constant of integration g of x, but the value of dp by dx is equal to this. Therefore, g dash x is equal to this quantity, and from this I try to integrate it and obtain that g of x is equal to rho x a square by 2 into x square by 2 minus ab times x, and plus there will be some absolute constant of integration, because now we have integrated both partial differentials dp by dx and dv by dy. So g of x will be equal to this quantity, and if I put down in the value of p, then the value of p that I obtain for this pressure field will be p of xy equal to all this quantity, where c1 is equal to some absolute constant. So the velocity field for an incompressible flow has been obtained, and it is not affected by absolute magnitude of the pressure, but it is affected by the pressure difference dp by dx, dp by dy, and so on. You can see that if I differentiate this with respect to any of these constants, in fact this C1 is not so important now. This will disappear, and therefore we have this value of P, and the gradient of pressure actually is important for occurrence of fluid motion.